So as Cash said, I'm from the Mechanical and Industrial Engineering in Northeastern University, and this is work that I have been doing with one of my PhD students, Aybike Ulusan. And what I'm going to talk about today is a specific problem on restoration of services on a disrupted infrastructure system. And what I will show is really, I'm going to talk a little bit about operations research, industrial engineering type of modeling, but also merge that with some network science type of approaches to come up with some heuristics and resiliency insights on some instances driven from these two types of approaches. Okay? So first of all, I know that for this class, maybe it's, it might be too much of an introduction that you might be experts on this. But let me just to kind of give you my take on it, let me maybe repeat a few things that you might already know. Okay? First of all, critical infrastructure systems enable the functionality of many services. Okay? So our look at critical infrastructure systems such as transportation systems, communication systems, energy systems is kind of an enabler of services. Okay? And any disruption within the infrastructure system may have an adverse effect on the delivery of the services. Okay? So affecting the society that we live in. So our take on critical infrastructure is kind of an underlying network, okay? Kind of an underlying network over which we have another network of services that we provide some kind. It could be healthcare services, it could be delivery of food, it could be any other kind of a delivery distribution service system that you can think about, which means that you have some supply and demand locations around the network, and you want to allow for connectivity between these two locations, okay? And it can only be done if there is a if you can actually connect a supply to a demand node in the service network, if and only if you have a path between those two nodes in the infrastructure network that's underlying the service network. Okay? As I said, for the service network to be operable after an event that's disrupting the infrastructure network, for the service network to be operable, we have to recover the infrastructure network. Okay? And it turns out that recovery on the infrastructure networks is a complicated task because, first of all, as we said, they're kind of interacting layered networks that we're concerned about. They're usually multi-periods, right? We're not usually thinking about doing work in just one go, but there are multiple periods, and at each period you have a given amount of resources which you can use for recovery type of activities. And the thing that I want to emphasize here, which is different than some of the other approaches, is that during this talk, my goal or our goal in this research is to recover or restore a subset of the components in the infrastructure system to enable services. So it is different than saying that we're going back to complete recovery where the entire infrastructure network is recovered. Okay? That's not the goal. This talk is geared towards responding and the immediate recovery after an event, which means that I just want operability in the service network. Okay? So I don't have to recover everything on the infrastructure. Actually, it turns out, this problem turns out to be a little bit more complicated than the complete recovery. Okay? And today, I'm going to be talking about a case study on post-disaster debris operations to enable emergency services. Okay, so we're going to be looking at a specific type of a disruption on the transportation or the road network. And why do we care about the debris? Okay, I mean, first of all, I care about the debris because I've been working on it for more than half a dozen years. It was first presented to me by the Atlanta Fulton County Emergency Management Agency as saying that, you know, after a debris event happens in Atlanta, one of the big questions that we're faced with is the order of which roads should we go and open up first. Okay? So that it kind of started from there, And then I have been working with FEMA and the Army Corps of Engineers within the US and different local emergency management agencies to look at this problem and variations of this problem that I'm going to talk about. But, I mean, why do we care? Kind of taking a step back, debris actually that is generated after a significant disaster or a disruptive event, such as a hurricane or an earthquake, is important because it has both very significant short and long-term impacts, okay? On the short term, it basically blocks the roads and makes travel hard or even impossible. So if you're thinking about emergency response and bringing, let's say, emergency response personnel to the people, search and recovery, bringing it supplies, having debris on the transportation network or the roads is a big problem for these kind of activities. Okay. On the long term, if we don't take the debris out of the impacted area and process it properly, it does have, debris has very significant public health and environmental effects to begin with. But also, I mean, imagine having debris on your yard. The neighborhoods never get back to normal until all the debris is removed from the neighborhoods, okay? So it has, first of all, we care because there is an impact, important impact. Second, we care because debris is a big deal. What I mean by that is the fact that just after a significant weather event, the amount of debris or the waste that is generated could be equivalent to multiple years of solid waste generated in the same area. So imagine like solid waste, how to process it, how to take care of it is a big, important operational problem in urban planning and urban management. Imagine generating that much waste. Imagine generating waste that's equivalent to a few years of solid waste in a couple of hours. Okay, it just becomes operationally a very daunting problem to handle. Okay, so for example, after Hurricane Katrina, the amount of debris that was generated was equivalent to about filling the Louisiana Superdome about a mile high. Okay, so it's a lot of stuff that you have to carry out of the city, you have to take care of it, and so on. The third reason why we care, it's also a very costly and complex process. So according to some estimates, about 1/4 of any disaster recovery operations cost is related to debris activities. Okay? So managing this process better and more efficiently will also have a significant impact on disaster recovery costs. And what we have right now is that there are federal and local guidelines that are focused on what to do and what to do, okay? And even this came out after Hurricane Katrina, where there was a big problem with the debris and nobody was prepared for. So now there is a big push and incentivization for local emergency management agencies to think about what they will do. So it's called the debris planning. Like they do debris planning. They do have plans for debris recovery. But these plans never really focus on how to do it, which is, as industrial engineers and operations research people, that's what we think about, right? How to do an operation in a most efficient way and effective way. That's why we started to work on this problem some years ago. So when we say the debris operations, we can really think about it along the disaster timeline, which means that pre-disaster, there are certain things that we have to do before a disaster. There are certain things about the debris that needs to be done right after a disaster in the response phase. And then there is also a certain number of activities that needs to be completed after after the first response when we're thinking about recovering of the communities. Okay? So for example, in the pre-disaster area, the type of activities that needs to be done really is more about the planning stages. For example, planning where should you, if you have a big debris event, where should you put it? like in Puerto Rico or like in Haiti after the earthquake, in island nations specifically, this becomes a big problem because you have a lot of waste and you're on an island and there is no place to put it. So in Haiti, after the Haitian earthquake, for example, at one point they started dumping things into the sea, creating a huge environmental problem. Okay, so all of these kind of thinking about where would you put the debris management sites, who would like kind of getting into pre-contracts or contractual agreements with companies and teams who would actually come and do the debris activities are things that needs to be done before an event happens. At least these things need to be thought about. During the immediate response, really the biggest operation that needs to be done, and which is the topic of my talk today, is the debris clearance activities, which means that at this stage we only consider going through the roads that have piles of debris on it and pushing it to the sides. Okay, so the only goal is to actually opening up the roads for traffic, okay, for connectivity. And we don't really care what will happen to the debris. We're just pushing it to the side so that you open the roads. And this is in general called debris clearance. And then in the last stage, the problem becomes debris collection, which means that you actually go with now trucks and collect the debris from where it was pushed, and then carry it to debris reduction and recycling sites, and then do the final disposal. Okay? But today's talk, as I said, is going to really focus on the debris clearance as an example of restoring the road network. So we're really not thinking about maybe building the roads, but we're just kind of cleaning the roads from the debris. Just now getting into the problem definition to be a little bit more specific, the objective is to determine a sequence of block roads to be cleared over time. So all we care about is to say which roads should be cleared first. Okay? And our goal is to make sure that the demand for relief is satisfied in a timely manner. And we have a certain amount of limited resources to be used at any given period for debris clearance. And then to connect the demand for relief resources to supply by efficiently restoring the emergency service network, we need to really understand what is demand and supply. We can think about, for today's talk, that the demand is people in need that are dispersed in this affected network. You can think about they exist on the nodes of the network, okay? And the supply, you can think about it as critical facilities such as healthcare clinics, fire departments, or point of distributions for relief commodities, and so on. And we also assume that the supply is distributed among the nodes of the network. Okay? And then, as I said before, currently there is no systematic procedure for how to open, what's the prioritization of the roads to open. Okay? So there are very, very generic guidelines that is established by FEMA and some of the local management agencies. And they usually just, so if you know a little bit about transportation networks, usually the roads are classified into, I think, 4 or 5 types in terms of their priority. So basically what FEMA guidelines say is that just go with that priority and open up the roads that are top priority. But you can imagine what might be wrong with that. I mean, a road can be top priority before in an infrastructure that is not disturbed. But in an infrastructure that is disrupted, opening up like a highway that is not connected to anywhere will actually bring in no benefit. Okay? So what we claim is that kind of a prioritization structure is especially just looking at the importance of the roads before a disruption happens and demand and supply is realized is meaningless. And I will show you some computational results towards the end to kind of emphasize that. So I usually like to give us some of the recent examples. So of course, we had a terrible hurricane season over the last year. And one of the most significant ones was Maria, which hit Puerto Rico. And Unfortunately, because of the debris situation, there were really a lot of cases reported where debris arrived at the airport or the ports but couldn't get distributed into the island to the needy population for days. So here, I mean, in one news report, it was said that 10,000 crates, including fuel, water, food, and medicine, were stranded at the ports for days. And also, due to the damage and the debris on the roads, many residents were trapped actually in their, and then they couldn't reach, they were trapped in their localities or in their houses and then couldn't reach to public services again until the rescue teams reached them. Okay? So in that kind of a situation, our goal, as I said, our goal is to connect these people who are in need to the supplies. Okay? And we want to do this efficiently. So the first thing, if we're trying to write a mathematical program down for this problem, is to think about what should be our objective function. And here we choose an objective function that emphasizes the timeliness connecting supply to demand. So what this curve here means is that if we, so the y-axis is the benefit that we incur by connecting one unit of demand to one unit of supply, but then the x-axis is it represents the time. So this curve means that the earlier we connect a demand to a supply, the benefit we get from that connectivity is much higher than the connectivity established much later in the periods. Okay, so we really, really want to emphasize the fact that early is significantly important. And in cases, this could be a life or death situation. Okay. So then what I'm going to do now, I will go through the formulation for the mathematical program for this model, although I'm not really going to emphasize the mathematical model because at the end what we propose is really a heuristic that has nothing to do with the mathematical program, but we compare it to this. Okay? So the way that we write the debris problem has several classes of constraints. The first class of constraints we call the balance constraints. So what they really do is kind of keep track of how much demand that is not satisfied at each node at a given time period t, how much remaining supply is left at each node at a given period of time t, and then take care of the flow, which is really the way that we connect a supply to a demand node at two different nodes. Okay? So this is, you can think about this as supply, demand moving to supply, or supply moving to demand at the network. And then the additional thing that connects the infrastructure network to the service network is are these constraints, which tells us that an arc ij can only be used at a period after it is completely restored. Okay, so this gamma is really the variable indicating the first period that the edge is fully cleared. Okay, and then the next class of constraints really deal with the recovery resources we have. Okay, the first class was about supply demand of emergency, emergency crew or the service aspect of the network. Second part is really about the recovery of the resources that are available for the recovery of the infrastructure network. And here we assume that there is really a given amount of debris, given amount of resource required to repair an edge, which is correlated with the debris amount on it. And then we say that basically we kind of accumulate how much debris is removed from an edge at each given period until it's completely removed. And then at the time period that the debris is completely removed, we say that, okay, now we can consider this edge as open, okay, as cleared. And then we also have to make sure that the amount of resources that is available at a given period t is not violated by or the amount of resources that we use for debris clearance activities at a given period t is not greater than what we have available. So you can think about these as trucks, number of people, cranes, what have you, whatever the resources are. You can really convert that into maybe per hour, how much you can remove per hour, or whatever the context is. You have to do some conversion in terms of your units, but really the most important thing is to understand that, let's say each day or at each half a day, you only have a certain amount of resources that you can use for these clearance or recovery activities, okay? And then, of course, we have a bunch of integrality, non-negativity type of constraints that are not so interesting. But what I want to do now is to connect that, connect the problem with some of the literature, and then connect everything to something that has really not been considered too much in this area, which is network science, okay? So first, within the operations research literature, of course, the problem of network design and scheduling crews is a problem that is well studied. And mathematical models that are similar to what I've just shown exist everywhere. It's not so original, right? What we know is that they are hard problems to solve, right? They're hard mixed integer programs. They're hard to solve. They usually take a long time to solve for realistic instances. Okay, one thing that I forgot to tell you about our mathematical program and the nature of the problem that we have is that so one thing that's important in debris clearance type of problems is that you actually have to think about the fact that you cannot go and clear a road that is not connected to any resource, debris clearance resources, right? If you think about a city that's completely covered with debris, okay, and imagine that all the resources are on the boundaries. If you really think about the operations, you can only start the operations on the boundaries, right? Because you cannot really fly over and go into the middle and start clearing there. So one thing that you didn't see in my formulation was any explicit constraints for saying that you can only open up rows that are connected to a resource, okay? And in our paper, we show that actually you can take any optimal solution that might open up something in the middle that's not connected to any resources and convert it into an equivalent optimal solution where that connectivity constraint for resources is satisfied, okay? So maybe that's kind of one of the more interesting parts of this problem compared to some of the others that existed, some of the other network design and scheduling literature that exists in the operations research literature. So there's a lot of literature on this, and I'm sure some of you know some of these papers. And we also have a couple of papers that are looking at mathematical models, looking at some complex heuristics, and so on. But then one of the problems that we always run into when we really put our operations research hat on is that these solution approaches are not so useful for FEMA or Army Corps of Engineers. When something happens, it's a clunky model that requires a lot of data, kind of sophisticated algorithms to run them, and so on. So then we started to try to kind of simplify. Like we were saying, okay, how can we actually solve these problems maybe in a faster manner that's not so hard to understand? I can actually explain it to somebody who doesn't really maybe have an operations research background and runs fast, okay? So then we actually turned and started looking at some of these network science literatures, okay? And I know that there is a group of people who work on network science measures and so on on this campus and in your department. But usually in traditional operations research literature, you don't see too much mention of network science type of ideas for solving operations research problems, okay? So when we started looking at network science literature, what we have found is that there's a lot of literature that looks at characteristics that characterizes random, large-scale random networks, looks at network vulnerability, network functionality as the size of the largest connected component, and so on and so far. But what we have seen is that most of the network science literature is really not focused on the service component. It's all about connectivity. Okay? They're really not looking, they're worried about what is the largest component, but imagine a scenario where I have no service demand in this largest component. I couldn't care less if it's connected or not. Okay? So then what we said is that can we actually take these operations research problems that look at service delivery in disrupted infrastructure networks and use some of the simpler network science ideas to come up with algorithms and heuristics that are easy to solve. So our contribution, we actually came up with a network science-based restoration heuristic, and we use these heuristics to actually assess the criticality of the disrupted service network components. And then using these ideas, we actually run a bunch of computational tests trying to understand the resiliency implications of different types of infrastructure networks on service delivery. Okay, so that's what I want to talk about next. First, the proposed idea, and then computational results that lead to insights about resiliency. Okay? So in network science, one of the very classical and easy measures of understanding the importance of a node is called the node betweenness centrality. Okay? And what it does is the formula is this, but what it does is it really looks at all pairs of nodes, ij, in a network, okay? And it counts the number of shortest paths between the node I and j, okay? And shortest usually here means that the fewest number of arcs, okay? And then it says, okay, so for me to understand the number of, the importance of node P or node PK, then I want to look at, I want to count the number of paths, number of shortest paths that go between I and j that go across node P, okay? So I'm kind of saying like, among all the good paths that go from here to there, how many of them goes through this node, okay? And then I count that for all pairs of nodes, right? So if this number is high, obviously what that means is a lot of good paths between different pairs of nodes depend on this node, okay? So this node is critical to this network. So it's an idea that makes a lot of sense, right? I mean, it's really, so that's what I mean, like some of these network science measures are things that make a lot of sense. I mean, you know, you can really explain it to somebody who doesn't have a lot of mathematical programming background. Okay, so then, sorry, just to give you an idea, and I think I've already talked about this, but as an example, in this network, the two black nodes would have the highest betweenness centrality because they lie on every single shortest path between any of the nodes, actually. Sorry, not between any of the nodes, but actually, so like if you're going from here to here, you have to go through this node, right? If you're going from this side to this side, then you have to go from both of them. And on this side, if you're going from here to here, you have to go through that one, right? But they are, if you look at the betweenness centralities, you would find that these are the two nodes that have the highest centrality measure, okay? Of course, the problem is, if you just look at this network and the betweenness centrality measure, you would think that these two nodes have the same importance, right? But now imagine a service system that lies on top of this infrastructure system, where the only supply and demand are among these three nodes, okay? In that case, obviously, this node will actually have no importance, okay? And this is kind of the point that we wanted to take care of, saying that, okay, network science is great, and it gives us a lot of simple measures to really think about criticality of network components, but we have to modify these measures for them to make sense for service delivery, okay? So that's what we do. And I'm going to go through this pretty fast, but we make about four different, four variations or four modifications on the existing centrality measures. And here's like a short summary of the type of different things that we have changed. First of all, we calculate the shortest paths with the debris amounts as the kind of the cost of that path, right? And the reason for this is I don't really care how many road segments I go through as long as those road segments were cleared, right? I mean, it's just really here what we're assuming is that travel on the road network that is open is instantaneous, right? That's just fast. So what I really care about is, so whenever I'm kind of calculating the length of a path, I really assume that the length is equivalent to the debris amount on the roads of a path. Okay? So it gives me a measure of how much resource I have to use to clear up this path from here to here. Okay? So a path with only one edge could be considered longer if it has a lot of debris on it than another path that has 5 edges with very little debris on it. Right? So it's kind of saying that giving priority to those paths that are easier to clear. Okay? The second modification that we have done is that we don't consider all node pairs in the network, but we only consider node pairs that are supply and demand nodes, right? Because I don't care about connecting two supply nodes to each other. I don't care about connecting 2 nodes that have no supply or demand to each other. Okay? And then what we do is we scale the shortest paths with their weights. And then we also, the last modification we do is actually we give some weights to the shortest paths between nodes with larger supply and larger demand. Okay? So the idea is that it's not only important that I have a supply on this node and a demand on that node. I should care more if I have a supply node that has 100 units of supply versus another supply node with 5 units of supply, right? I should try to open up things to the supply nodes or to the demand nodes when the supply or the demand are higher on those nodes. Okay? So we end up with having a slightly more complicated centrality measure. Okay? But it reflects some of the important aspects of a service network. Okay? And so I'm not going to talk about this too much today, but of course, there are certain aspects of calculating the centrality measure that are computationally challenging. Okay? And we have done quite a few kind of heuristics and applications of different ideas to actually gain computational efficiency. For example, we have done things like if I'm looking at a network component that is all connected, I can kind of combine it or condense it as just one node, right? You don't really need to have a bunch of nodes that are connected to each other as represented as separate nodes, because I don't care about as long as everything is connected to each other, I can just consider that to be one. Okay, so we have done those kind of simplifications in our networks. We have used certain types of data structures to be able to calculate these centrality measures, because we actually calculate these measures over and over again in the algorithm, which I'm going to show you next. Okay. Okay, sorry, I actually forgot to say one thing that is important, which is, so if you remember, going back to the lecture, we're trying to decide which rows to open in what order, okay? But these centrality measures are for nodes. So what we do is to calculate the importance of an edge rather than 2 nodes, we simply just add up the importance of 2 nodes, of the 2 nodes that are on either side of the edge, okay? So that we come up with this service network edge between a centrality measure, okay, for a given edge. And then we actually ended up having a quite simple heuristic, and simple meaning that it's idea-wise is simple. Computationally, to make it efficient, we actually had to really think about good algorithms to implement, good data structures to implement, some of these tricks like collapsing all the connected components into one node type of reduction strategies. But the main steps of the algorithm, basically what we do is at the beginning of each period, we calculate the edge between the centrality for all the roads that have debris on it. And then we just choose the edge with the maximum centrality measure, and we clear it. Once we clear it, we satisfy the newly connected demand and incur the benefits from that. Then, if you can imagine, once you do that, all the centrality measures change, right? So you have to go back and recalculate all the centrality measures. So this is what I mean. Idea-wise, these are simple ideas, but to implement them in an effective way, actually it takes quite a bit of thinking about how do you write your network, how do you do your data structures, how do you write your algorithms so they're computationally efficient. And then we do this until all the clearance resources are used in the current period, and then we advance to the next period, okay? So very simple. The challenge is how do you actually computationally update between the centrality over all the network nodes or edges at every time you clear something, okay? And you know, again, I'm not going to get into all the details of how we've done that, but we've basically used some data structures which identified which node pairs are getting affected, okay, by a clearance activity, okay? So using those ideas, we were able to bring the heuristic to a level of enough efficiency. So then, and that's all I'm going to say about the heuristic. Are there any questions? Yeah.
In the betweenness measure, do we really take into the physical distance between the nodes?
No, that's exactly what I was trying to say. I really don't, for this context, I don't care about the distance. I only care about how much debris exists on that road. So if the road segment could be 1 mile, if it has no debris on it, to me it's just I collapse the nodes even.
So what if 2 roads have equal amount of debris, but 1 road is bigger in length?
I count it as equivalent, okay? Because I mean, it's a very good question, but here the assumption is that you don't really, I mean, we're looking at a metro area, and then, you know, going half a mile versus a mile on an open road is not really the issue here. It's more about just how much work you have to do to clear that road. Okay, thank you. Any other questions? Yes?
From a practical perspective, was the city of Atlanta okay with estimating the amount of debris?
That's a very good question, and I would say that's the biggest challenge, current challenge, because, and maybe we should talk about this at the end of the lecture, but that's the biggest problem right now. After a significant event that creates a big debris field, the biggest challenge is nobody knows exactly how much debris exists on roads, okay? So actually, after the Oklahoma City tornadoes, right? There were rather big Oklahoma City tornadoes a few years ago, right? I was actually on a call with a group from FEMA in which the manager of the group was saying that, you know, I would give my horse to anybody who can figure out how much debris exists. And we were just talking about and brainstorming about how do we actually get a good estimate of the debris amounts on the streets. And the types of solutions we were talking about was maybe we should give people all iPads or like handheld, you know, something that they can take actually pictures of and email it. So right now, what happens is the current state of the art is obviously there are flyovers after a very big event. There are flyovers where like a lot of pictures and imagery are, you know, like taken of the affected region. There are reports, and as you start clearing, you actually start learning how much there is. But it's all estimates. So I'm not talking about this today, but we actually do have a paper that's on looking at uncertainty and like how do you actually make these decisions under uncertainty. But that if I was presenting that paper here, I would be talking much more about math rather than here's a heuristic that you can apply, because I don't think that what we present in that paper is applicable in the real world. It's more of a proof of concept when you actually have uncertainty than what do you do? You know, how do you handle things? So I would say that's where the state of the art is right now, really understanding what you can do in an environment where you don't really know how much exists on the roads. So what are actually, after the set of hurricanes that happened over last fall and until December, I've been talking to quite a few people in GIS, like who do research in GIS and mapping and so on. And one thing that I couldn't believe and found very frustrating was the fact that after Maria and after the hurricanes in Irma and all of those hurricanes, there's a huge open mapping community, right? And they kept telling me there's an open mapping community. You can actually go in. You can get the data, because we were there like we want to get the data. And actually, the disappointing thing was, if you go into these maps, they were all about the pre-disaster maps, and it was the whole mapping community was working on making the pre-disaster maps more accurate. So they believed that was the first step to do. If you look at, so the state of the art there is really trying to figure out some imaging technology and other things where you actually can figure out the difference between two images, like pre-event and after-event. And what can you say about the damage or the debris amount and so on the road network? But I really don't have a good, it's a great question. But there is, as far as I know, there isn't really a good answer to that challenge at this point. I really think as an operations research and industrial engineering community, we do need to work with some of these imagery people, GIS people, open maps, and so on, to actually bring that community to do something more meaningful for decision making. That was the thing. What I've observed was that they were doing a lot. There was a lot of open source mapping activity that was going on, but not much of it was geared towards what's the important thing for making a better decision. So stepping back to the heuristic, assuming that we live in a perfect world and I know all the debris amounts on every road segment, we've done a bunch of computational testing. And again, really, we've aimed at a couple of different issues during this computational testing, some of which was understanding of resiliency aspects of different types of networks. So to do this, we've looked into two types of instances, or we generated two types of instances. The first one were randomly generated and with two types of topological features. One was grid networks, which kind of represent cities that are kind of more modern cities like Manhattan, right? And we also looked at irregular networks, which is kind of more randomly generated and has no particular structure. And then we looked at, we also varied the structure of these networks, meaning that we looked at how elongated these, let's say, cities or the graphs are, because we thought the diameter of a graph also made a difference. Like, we wanted to understand if the diameter of a graph made a difference in terms of the resiliency of that kind of an infrastructure. We also looked at the distribution of supply nodes, like hospitals or emergency services, service providers within the graph. And we looked at what if you have a single supply source versus multiple supply sources? Because as you might imagine, if you have a single source, you can have all your supply concentrated there. If you have multiple sources, you'll have to decide how you actually allocate your resources through these multiple sources, right? So if you think about it, if you have multiple sources, you can say that, okay, I can put some in every neighborhood and the accessibility will be easier, but then you kind of limit the supply amounts, and when you kind of, like, you have to distribute these supply amounts. And if you end up putting the wrong supply amount in a location where there isn't that much demand, then that might actually work out worse than having just one supply node with a lot of demand put into a central location. Okay, so these were kind of the type of questions that we wanted to see if they had any or type of issues we wanted to see if they had any implications on the resiliency of a, let's say, a city. Okay? And then, other than the randomly generated instances, we also looked at two actually realistic settings, taking Boston and Manhattan as our examples, because Boston is kind of this irregular network where you have spaghetti roads all over the place, and Manhattan is kind of an example of a grid network which is much more organized. And for these instances, we use the HAZES software, which is a software that FEMA uses to run simulations of an event. And it's really, if you don't know about it, it's really a very effective software where you can basically say, if I have a category 4 hurricane coming into Florida Panhandle, show me, like, simulate the damage on the road, the people how many people died, how many people are injured, what's the damage on the power network, and so on. So we use the HAZES software to generate these somewhat more realistic instances. And we also looked at kind of the level of disruption, saying in one, varying, saying that half of the network is disrupted, meaning that half of the network's roads had debris on it, or 80% of the network's rows have debris on it. Okay? So just to show you, these are the types of graphs we looked at. The ones on the left are, or on the right, are the grid networks. As I said, I mean, we really cared about this diameter of the graphs. So like, the top graphs for both irregular and grid networks, for example, can represent a city that's a coastal city, such as Miami, or a, kind of a populated area that's basically along the coast, versus maybe a more of a square city could be something like Oklahoma City, right? Which is, although I'm not sure, like I'm saying this, but I'm not sure if there is a river, right? There is a river. Is it along the river? Oklahoma City, is it? Around, so yeah, so I mean, so this would be more like a, so I'm not sure, maybe Oklahoma City is like that. I have to look at the map, I'm not really sure. Okay, and then these were the instances that we, this is how some of the instances we generated for Boston and Manhattan look like. So this is Boston, and this is Manhattan. So the red crosses are the health centers. We actually use the real locations for hospitals and healthcare centers. And these circles represent we actually simulated an earthquake scenario for the debris event. And these show the epicenters of the earthquakes. Okay? Questions about the instances? And then also the way that we created the demand amount. So I showed you the supply points. So how did we create the demand? We actually looked at the population in the census tracts. And also we looked at how much debris was generated by the HAZES software. And we said that the demand at the nodes in a city should be proportional to both how much debris is generated there and the population. And the reason for that is, if we assume that there's a lot, if we see that there's a lot of debris, we made the assumption that there will be more people, a higher percentage of the people in that census tract will need aid. Okay, so that's how we generated it. So these blue dots that you might be able to see over there are the representations of the demand nodes. And one thing that I want to point out here is that the distribution of the nodes here, the blue nodes, is somewhat different in Boston and New York, okay? So I want to kind of emphasize the fact that, or I'm going to come back to this, but I want to emphasize it right now by saying that really we cannot just look at the topology of the infrastructure network. It really matters where these blue dots are. And where these blue dots are is not going to be just based on population characteristics, but it's going to be created after a disruption happens, like after an event happens. So it is actually, so our hypothesis was that it is actually very hard to make big statements about resiliency and this and that without considering actual scenarios of disruptions, okay? Because the way that demand and supply and demand and disruption is going to propagate in the network is really going to have a big impact on how fast you can recover that network, okay? And it's very hard to say that before actually something happens, okay? So let's see if the computational results support that claim. First of all, I'll show you a boring slide. This is just a slide that looks at the quality of the heuristic that we presented. If you remember way back when, I actually presented a mathematical program too, which solves the problem to optimality. So we compared the quality of the solutions that were generated by the heuristic versus the quality of the solutions that were generated by the mathematical program. So first of all, we look at the grid networks. What we see is that the heuristic actually stops within less than a second. Okay, so it's quite fast. And then the optimality gap that we calculate, and the way that we calculate the optimality gap is actually the upper bound. It's the gap between the upper bound that's found with the mathematical program. And sorry, actually, just want to emphasize the problem that we're solving is a maximization problem. It's not a minimization problem because we're trying to maximize the benefit that we incur by connecting supply to demand, okay? So basically what this table is trying to say is that the heuristic finds some solution in less than a second. The MIP runs for 24 hours, okay, reaches the best solution within a few hours, and the optimality gap that the MIP and the heuristic has is not so different. Okay, so these were, like, even for these very small instances, the MIP was not able to find optimal solutions for the grid networks. And what we found with the heuristic was really, quality-wise, was very similar to what we were able to find after 24 hours with the optimal approach. The second, and then this was the grid networks. If we look at the random or the irregular networks, it turned out that solving the irregular networks to optimality was much easier, which is kind of something that you usually expect. It's easier to run exact optimization approaches on randomly generated graphs in general. And so what we see here is, though the conclusion is similar to what I've shown you in the other table, that is the heuristic solves the problem or finds a solution within less than a second. The optimal approach finds the optimal solution in this case within less than an hour, or in minutes really as well. And then, but the good thing is the solution that the heuristic finds is always within less than 1.5% of what the optimal solution was. So after running, and I'm just showing you a limited set of the computational experiences, but what we have seen is that the heuristic performs really well. I mean, it's really not doing much worse than the optimal approach, so it's something that can be trusted. And it runs really fast. Okay? So then we started looking at resiliency implications, okay? And to do that, we actually used a concept that's well known to the resiliency community, which is these resiliency curves. And what this, the community usually use these resiliency curves to look at how do the quality of the infrastructure improves over time. Okay, how does the quality of the infrastructure improve over time? And in our work, we assume that the quality of the infrastructure is equivalent to the percentage of the demand that is connected to the supply at that period of time, right? So here, so for example, the quality of the infrastructure here was 100%, meaning that everything was connected, we had perfect service, and then something happens, the network degrades to 50%, meaning that 50% of the supply is not connected to the demand, And then over time, we see service improving until at point T1, all supply is connected to demand. This doesn't imply that all the rows are recovered. It just implies that all the services is being satisfied. All the service needs is being satisfied. So based on that, we started running a bunch of experiments on different types of graphs. And here are some of the conclusions that we got. The first set of experiments that we ran was looking at distributing debris over the network randomly. Okay, so every rod had an equal likelihood of having some debris on it. In that case, what we found is that the best strategy is to have multiple supply locations. Okay, so which is maybe not so surprising. And the graph on the top is for grid networks. The one in the bottom is for irregular networks. And what you see is that the top curve, which means that it's the curve that gives us the best resiliency, is when we have multiple depots or multiple supply locations with all infinite supply, of course. When we limit the amount of supply and distribute it on these multiple supply locations, the resiliency is still pretty good, right? We don't get too much degradation. However, then we try and see that what if we have a single supply location? What we see is that, especially on irregular networks, if this single supply location is farther away or on the edges of the graph, has a big effect on how the resiliency of the network is. Okay, so what I'm trying to say here is that if we have a hospital and it's on the edge of a city, I mean, obviously the resiliency is going to be harder, which means that we're going to have a harder time, or it's going to take a longer time for us to connect all the demand to this hospital location, which is on the edges of a network. Okay, if we still have one hospital but it's in the middle, then it's a little bit better, right? The best is having everything kind of distributed. For irregular networks, especially with larger diameters, right, these elongated networks, they are more sensitive to supply, where we position the supply quantities. Okay, and it kind of makes sense, right? If you have an elongated network with a large diameter, if things are on the edges, then you are really far away from some of the other, some of the demand locations. So these are kind of expected results. And the thing that I would say that's kind of most interesting here is that we find that the grid networks are much more resilient, consistently more resilient than irregular networks when the debris are distributed randomly at the graph. Okay, so what we see here is, so now the lines represent each of the graphs. And what we see is the ones that are on the top are the grid networks. Okay, so the resiliency, the recovery of the grid networks are happening much faster than the irregular networks. Okay, and this seems to be true both for supply locations, multiple supply locations, and for single supply locations. What we see is that the difference is larger whenever we have a single supply location. These are not so crazy results, and I'll pass that, but these are all kind of showing what I've just said. Now, I think the thing that's more interesting is, so we have run all our experiments and we got all sorts of insights on these irregular networks and grid networks randomly generated, where debris is randomly uniformly distributed, okay? And then we started running things on realistic settings, okay? And what we have here, this is the resiliency curve for Boston, and this is the resiliency curve for Manhattan, okay? So the lines that you see here, first of all, we wanted to understand what is the contribution of our idea, of our heuristic, okay? So first, on these realistic instances, we tried a couple of different other alternative ideas compared to our heuristic. So the first one, the blue one, is the opening up the roads based on road prioritizations, which is what FEMA suggests at this point. And as you can see, it pretty much has the worst resiliency curve, okay? The second one is opening up the rows based on the between the centrality measure that network science proposes. So not looking at any of the service aspects, but just connectivity, or like kind of understand or equating the importance of a node to the connectivity. Okay, and then the yellow line is when we do our first modification. The red line is when we do the second modification, and then basically this dark black line is when we actually do all of the modifications that we wanted to do on the between the centrality and the final heuristic. So what we have seen is that consistently our heuristic gives a much better resiliency curve for different types of realistic instances. Okay, so that's one thing that we wanted to show. So the next thing that I wanted to show you, which is kind of the most surprising thing in this paper, is the fact that when I put together the resiliency curves of Boston and Manhattan, what I see is the following. The purple one is for Boston, and the blue one is for Manhattan. Okay, so which one is worse? Manhattan. Is this aligned with what I've shown you in the other? No, right? So Manhattan is a grid instance. Boston is an irregular network. And at the end of the day, what we have found, and I'm just showing you some experimental results, but we did many different types of computational testing. And what we have seen is that it ends up, what we see is that Boston ends up being a more resilient type of a city to this particular type of earthquake disruptions than Manhattan. And this was really, in the beginning, it was really confusing for us. We were kind of surprised. Like, we were really expecting Manhattan to come out better. Then we started saying, like, okay, let's figure out what happened. And here are some answers to that question. Basically, we said that, is it about the way that the debris was distributed? Okay, because when we added, so in the realistic instances, we didn't distribute the debris randomly at the roads, but we let an earthquake simulation actually distribute the debris on the roads, right? So these simulators that FEMA has actually takes into account not only the location and the strength of the earthquake, but it also takes into account the vegetation on the streets. It takes into account the building codes, the heights of the buildings, the materials. So it's really a very realistic simulation. So what we have found is that the debris amounts that came out of the HACES software was very different than uniformly at random. Okay? So what we concluded is that it's really important to understand what the real impact would be in terms of what is the disruption's effect on the roads before claiming that a grid city, Manhattan, is more resilient than Boston. It really depends on the building codes, how high your buildings are, I don't know, the vegetation on the streets, and so on and so forth. So to confirm this, we actually reran some of our experiments by randomly distributing the debris on the Boston and Manhattan roads. And in that case, what we have seen that Boston is the purple line, and it ended up being much worse than Manhattan. Okay? So here again, what we're trying to emphasize then to the community is that we really need to understand the impact of a disruption before we can really talk about resiliency, how fast we can recover, what's the right prioritization order, and so on. It really seems like we cannot make too many shortcuts by saying that, oh, like a network like this is more resilient than a network like that. It really depends on many other factors than just the topology of a network. Okay? And then we actually looked at the effect of supply locations. You know, remember, many, single, far away, and so on. And what we've seen is that they really didn't make, so this is for Boston and this is for Manhattan. And the blue lines is where you have distributed supplies. The purple is for at the boundaries. And it didn't really make a big difference. Okay? So that was also surprising. So what we have seen is that actually maybe the most important thing is what the disruption does to your infrastructure network, not really where you put your supply and demand. Okay? Again, this was something honestly surprising to us, but we have run many, many different types of experiments, and this is the conclusion we came to. As I said, we started this research by thinking about finding a simple way of a simple heuristic that can consider both the service aspects of the problem and also the aspects of infrastructure after the disruption happens. Okay? And this new heuristic, we think, performs quite well. It's something quite simple that we can actually explain to the stakeholders, and can be, if we have the debris data, it can actually run quite fast. And then at the end of the day, I don't want to repeat myself too many times, but we really concluded that although on randomly generated disruptions, we see a lot of correlation between the topology of a network and the resiliency implications. On realistic instances, we see that the factor that dominates the resiliency implications is the way that the disruption affects the infrastructure network. So then our really big insight is that taking into account post-disruption attributes are essential to develop efficient restoration strategies. So we claim that although it's important to be prepared and understand how you should run a debris operation or a restoration operation on your infrastructure network, I think we should also be equipped with these kind of decision-making tools that are simple and easy to apply to make more efficient recovery decisions after something happens. Okay, so it's important to have decision tools that can include after effects to make more efficient decisions. Okay, I think that's it. Okay, thank you.